Hi everyone.
Hi, this is Eric and Lin Sheng, and we will be talking to you today about methods for brain tissue segmentation in CT images.
And first of all, let me introduce four parts we're going to talk about today. So the first one is problem description and motivation. And second part is approaches. And third part is evaluation. And the last part we were going to talk about is discussion.
Okay, so our problem here is lies mainly in identifying sort of troubled areas in images, whether it's you know typically whether it's brain or other CT images or any other medical image. In this case, we're just looking at brain tissue, but these issues sort of span other um, applications of CT scans and other imaging modalities as well. Um, but um, so based on the traditional model, we have humans that are evaluating um, these images, and it's a very important problem determining whether or not um, there is a problem present in a medical image, and determining whether or not treatment needs to be undergone for a patient, and what kind of treatment needs to happen. So through implementing computer vision methods, um, we think it's certainly um, an advantage to aid physicians with new applications and new looks on this data. Um, so this should be able to increase accuracy, cut down with the amount of time it takes to make a assessment of whether or not someone needs treatment, and yeah, so it would just sort of improve everything overall. Um, and ultimately, it could end up allowing more physicians to look at the data, being that it would cut down on the time that it could take. This specific data set that we got is mostly was generated to look at brain hemorrhaging. Um, so that's like a blood vessel burst in the brain, and then there's blood present in the intracranial cavity. Um, so that's sort of what this data set is from, and that's kind of the perspective with which we're looking at. So for our approaches, first we first we found that we required to pre-process the CT images and the metadata, which came along with the DICOM images. Um, then we needed to apply initial thresholding to begin to isolate the brain image. Then we were able to extract the image of only brain matter via two methods, including connected component labeling with minor region removal, and the second method we utilized was region growing. Um, and we will be discussing sort of the differences between the two, and pros and cons. Um, then we had to carry out a correction of the identified regions, followed by um, the potential classification of tissue, blood, ventricles, and calcifications within the brain. Um, and then we'll talk about extracting useful data from these images, as well as the automation and improvements that can be made, and some of those that we looked at that may or may not have been successful, but we tried anyway. So this is initially what we were looking at when we read the DICOM images. As you can probably not see on the right there, it's a very dark image, and we were sort of initially wondering what was going on and what we were doing wrong with the data. And we initially found it out, but so we basically just used IMShow on our DICOM image that we initially got, and these images were based on the CT values, and the histograms show that it's a very unbalanced histogram. So so after we saw that, we read in the image using a contrast tool, so we could look at the histogram and adjust the values that we were able to view. We thought this would immediately sort of fix the problem, but as you can see in this image, it was still not great, being that all we could basically make out was the skull, and then the brain itself was just a shade of gray. But when we narrowed down the pixel values that we looked at on the histogram, we were able to isolate the brain values, the brain CT numbers basically, and we're just able to then clearly view the brain tissue. So then after that, we were able to programmatically adjust all the images in the same way. And then something else that we ended up doing, because we didn't really want to look at the skull or any other bone in our images, is that we applied initial thresholding to only display images that were, or only display pixels that were below the threshold value of bone, which was at a very high level. There are some smaller regions within the brain that did exhibit this maximum intensity value, and those were excluded in this step, but we implemented some methods later on that were able to correct this and brought it back in.
Okay, let me introduce one of the two main methods we're going to use. We're going to talk about today. The first one is region growing. So region growing is basically a pixel-based image segmentation method, because it can edit the neighborhood pixels into it if it's less than a threshold. But because it's very difficult to find the state points value as a low margin of the brain tissues value, because it's very important, but we can't find it in any time. So we change this region growing to calculate the average value of the regions to determine whether the pixel neighborhoods should be added or not. So this method does a great job at determining the boundary of the initial region by identifying where the average value changes. And so there are some flow diagram. The first we should do is select the set point, and then calculate the average value of the region, and check neighborhood pixels by using threshold, and then add pixels into region or not, or to do that. And finally, we repeat the calculation and get a good result.
So the other technique that we used to identify regions within the image was connected component labeling, and it's a pretty good method that's, I think, widely used in many computer vision and image processing applications. And the first step of this is just sort of a breakdown of the steps to implement um, connected component labeling. The first step is to create a binary image. Um, we need a binary image to work on this on labeling the components. And then we iterate through the image pixel by pixel, and we determine if the pixels of value 1 are connected using the pixels above and to the right. This slide says below, but we mainly use the pixels above and to the right of the current pixel. We don't use below because we're sort of moving row by row. So we're only interested in whether or not the pixel above us or to the right of us is part of the region we're looking at. And then as we're going along, we assign labels to each component. If the pixels adjacent to our current pixel have already been labeled, then our current pixel takes on the same label as those pixels. Or if we have found a new pixel that doesn't have a label yet, then we assign it a new name. And then if we figure out that later on in the process that two of these regions that we've already labeled were actually connected, then we go back and we correct the labels that we previously assigned to these regions to have the same label. After that, it's typically what's typically done is you end up removing small regions because most of the time in this method you're using it to identify something, and a lot of times it ends up being a large region. A lot of times it doesn't end up being tiny regions, but sometimes it does. The region removal can be used to basically, it doesn't have to be the biggest region or the smallest region. It could just be a region based on some sort of logic that you've defined. And then another step that can be done but doesn't necessarily need to be always, we ended up doing it, is to invert the binary image and repeat the process to include some areas in the region of interest that may have been excluded the first time around. And then there is an option as well to include a seed point in your connected component labeling, which automatically associates a region that you know to be a region of interest as a component that you're interested in. So here's a comparison sort of between the two methods. With region growing, you need to pick a seed point for it to work, for it to start. So it has an initial pixel value that's looking for as a threshold. Whereas in the connected component labeling, we don't need a seed point, but in certain applications, a seed point is helpful. Then with region growing, it connects grayscale pixels of similar intensity to the seed, and the connected component labeling determines if binary pixels are connected. So that's the fundamental difference sort of between the two. That and region growing isolates the region of interest based on the seed, but may miss some area due to seed point variability and boundaries. So something that's sort of similar with connected component labeling in that matter is that it sometimes doesn't recognize components that may need to be connected to your main region of interest as well. So they're sort of similar in that way, but I feel like connected component labeling has just a better way of dealing with that problem. And then a downside to connected component labeling is that it requires region removal to remove your smaller components, whereas region growing doesn't necessarily need that because it's able to stop at a well-defined boundary where the pixels that it runs into obviously aren't included in your region of interest. So something that we found that we needed to implement in this evaluation was a correction. So as we implemented these methods, we found that since the brain is not continuous in each slice, you can see in this slice that we have actually four or six parts of the brain, here, 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 and here. We only, however, were able to identify one using connected component labeling here at the bottom. Well, actually, this one is actually region growing, but also we ran into the same problem with connected component labeling. We were only able to identify this region. So that's a problem we run into initially, and that's why we needed to implement a correction. So neither of these previously discussed methods were good enough alone to get the result we needed. This is the example of our results using only connected component labeling, and as we can see starting here, we start to run into some problems when compared to the original images. So we can see that this slice is missing this front part, and then this slice is missing. This is the same slice that we were looking at on the previous slide, but it's missing up to 5 other portions, and then from there on down, we just sort of didn't get much useful segmentation at all compared to what we look at in the original images, where this image has 3 brain portions, and we didn't get any of them there.
Yes. We create a lot of methods, like only use region growing or only use blob labeling, or blob labeling and then use region growing. But however, in the end, the blob labeling correction produced the best results. So when do we use the correction? So actually, we use it begin as the first slice is less than the previous slice, even if the whole biggest blob is still the correct brain tissue. And we have 2 updating thresholds for to calculate the brain tissues blob components pixels, and it's updating because we change it in each loop, in each slice. It will be increased at the top of our head, and it will decrease at the bottom of our head. And after the thresholding, we rearrange the orders of different labels area and find the biggest or the second biggest blob to compare to the previous slice. Is that inside it or covered by the previous slice? And talk about the cover. Even if there is only 1 pixel overlapped by the previous slice, the pixel will remain and set all pixels which are in the same blob into the brain tissue. So sometimes the current slice is not overlapped by the previous slice, but we still same as a brain tissue. And intercranial matter can be classified by intensity. Oh, sorry, I forgot to show the code. Yeah. So this one. Sorry for that. Okay, so as you can see, it's our final code maybe, and it's about the blob labeling recorrection from here. So if the post image is larger than the current image, we do a blob labeling, and then to find the range and something like that to calculate it. And if there are some part out of the covered area, so we will put them into it and make it as a main brain tissue. Oh, right here, so it's in a for loop. So after this code, the threshold will be updating by divided by 3, and I think it's better, right?
Yeah.
So finally, there will be a mask in binary image, and it can just times the original image and get a good result. So the component. So intercranial matters can be classified by intensity or CT numbers for future analysis. And brain tissue tends to be gray, and blood tends to be light, a little bit white. And ventricles tend to be the darkest, like a black hole. And calcification looks similar to bone. So apply thresholds to images and make masks using relative shades. Just use
So if we want to do classification, if we ended up doing that after that, we'd be able to make some calculations based on those classifications. In one area that we looked at, we determined that we're able to calculate the volume of these regions, and you're able to do that through the DICOM metadata, which actually tells you the pixel size, which is the real pixel size of the pixel, and so that way you're able to calculate an area within the slice, and it also tells you the slice thickness. So that way you're able to actually generate an estimate of your volume based on how many pixels were assigned to that particular classification. In our particular application, we could look at the volume of the brain as a whole, or the volume of the brain in each slice, and evaluate that. So sort of something that we identified that could be useful for that is using the volume to evaluate severity of conditions and determine if further action needs to be taken based on maybe how much blood volumes in the intracranial cavity. Okay, so these are some things we sort of looked at as improvements on a basic model. The first thing we sort of looked at, well, one of the first things we sort of looked at was automating a seed point for region growing or for blob labeling. We didn't end up using region growing as heavily as we thought we would, so this became a little less important, but it was something we've still looked at quite a lot. And so for that, we looked at comparing brain slice sizes, so the size of the brain in each slice compared to other slices, and determining when we wanted to start using a seed point. And then we ran some calculations on the dimensions of that slice. So the minimum, maximum row and column, where the boundaries of that slice were, and determining some sort of ratio to where we should put a seed point. This was pretty difficult because sometimes even the head isn't quite perfectly up and down in the images, so the back of the head sort of shifts forward or backward as you iterate up or down the CT slices, and then also just any variability within where sort of that center point is where the brainstem comes in. That's certainly possible as well. So that proved to be fairly difficult in the application that we did sort of get working. We were able to get some of the to isolate some of the areas lower in the head, but it still proved somewhat problematic. The second thing we kind of looked at, which is really the first sort of idea we had come up with to automate, was the correction that Linsheng talked about, and we were able to implement that. It was there are ways where it can be done manually, where you're looking at a slice.
I think it's not right.
Right. Yeah, if you're looking at a slice of the original image versus your already thresholded and an already segmented image, and you think that your segmentation missed an area, then you can sort of tell your program, well, hey, I think you missed something, but we wanted to sort of come up with some logic within our code that just sort of automatically fix our problems, and I think that's an area that we did sort of improve upon. Something else we sort of thought about was automating the correction of classifications in a similar way that we automated the correction of the brain region, sort of by comparing where these classifications are present and whether there's continuity or not between slices. But this would also be sort of difficult because maybe you have calcifications in one slice but not in another. Maybe you have blood in one part of the brain but not in the other. So that'd be fairly difficult. Another thing that we didn't exactly look at, but we always think about because of its prevalence these days, is potential deep learning improvements, and being able to even implement something like where you do have like a several thousand data sets, maybe several hundred, where you're able to say, yeah, there's blood present here, and then have your program run through a new data set and say, determine whether or not there's blood in the brain, and how it compares to previous diagnoses that were learned by a neural network. So now we're gonna sort of run through some of our code briefly, and just sort of discuss it and display some of the results that we got. So one of the methods we used ended up taking quite a bit of time to run, just due to how it was coded mainly. But this is basically an improved version on what we showed earlier, which was this slide right here. So this was the this is the initial version of that slide using only connected component labeling, and then this is an improvement that we made, where we identified right here the first slice of the brain where the size of the component, the size of the segment had decreased between slices, and then we switched to the connected component, or to the region growing method for each of these slices based on a programmatically determined seed point. So we can see here it sort of worked, but like in this first slice, the seed point was off, so it just ended up identifying vertebrae instead of the brainstem, and here it identified vertebrae and parts of the skull instead of the brainstem, and here it just didn't do much of anything. And then as we talked about earlier with the correction in these two slices, we got very little useful data. So this was then later improved upon, again with the correction that we talked about earlier. And then just here's, I guess I can run through some of this real quick. But this is some of the code we had to sort of index our images and read them in, and set a threshold for size of a brain slice. And I'm going to go quickly through this because we did improve upon this code with another program, but basically in this one we were able to get tons of useful data to sort of compare and to improve our techniques, which is one of the reasons why it took so long to run, because we have, in each one of these structures, we have basically 31 separate images. So we're able to look at every step that we sort of took and assess it and determine if it was what we ended up wanting in our final product. Yeah. Yeah, so I'm going to turn it over to Lin Sheng to talk about our final sort of iteration, where we have correction implemented and we're sort of able to isolate everything we wanted to isolate.
And, so in this code, we use the blob labeling correction, not the region growing, and select a seed point at first. But yeah, manually, not automatically, but it's better. So let me run that. Oh. Okay.
Yeah. Hold on. I'm sorry. I need to change. I did change one thing. I changed the folder.
Yeah.
Go ahead.
Oh.
What else? What else did I reference?
Okay, never mind. Min2 of 1 is just a little bit difference between Min2, and so it's a mistake. So it's very important to make the image is seems in the same class, and so we have to do this to make it to see the image. Just like this. The only difference between those two. So first is load the images slice by slice, and let me find a seed point. This is the stem of our brain. It's at the bottom of our head. So sorry, bottom of our brain. So this is the first slice. and choose a seed point. And you can see our result in the red. Pretty cool. Yeah. Run it again. That's pretty cool. And find a seed point. Because the blob labeling is used a seed point to identify where is the first label, and remain it as we talked about before, and to remain it if it's not the biggest one. So that's why we can get a good result at the first slice and several slices above it. Okay, back to our PowerPoint.
Yeah, so now we're going to discuss we're going to recap and discuss our initial goals and sort of how our code ended up measuring up to those goals, and maybe some areas where it could have been better, or some things that we tried and maybe things didn't pan out. So when we were initially creating a project proposal, we were unsure how much time the brain segmentation would take, so we set several stretch goals in case the segmentation was fairly easy, which it turned out not to be. So we ended up doing only brain segmentation, and it certainly provided us enough of a challenge and enough areas to sort of improve upon and just try some more difficult methods. Another thing is we just evaluated one case. We weren't able to fully evaluate the effectiveness of our code in a setting where we need to look at multiple patients' CT scans. So it's certainly possible that there are shortcomings that we are not able to identify just due to variability in data sets. So we feel in general that our code did a good job at accomplishing the goal of sort of isolating the data we wanted to look at and giving us a better data set to sort of make an evaluation based on. And then so some of the improvements that we tried to make didn't exactly pan out, and some of them did. As we sort of discussed, our initial findings, none of them really worked to the degree that we wanted them to, and then we tried using both those methods together, and that even came up a bit short. But in the end, we're sort of able to bring it all together and come up with a product that was able to give us all of the brain segments that we needed, and yeah, there were some other improvements that we tried, like the seed point automatically being picked, that sort of worked but didn't quite yield the results that we wanted, as an example. So yeah, that's sort of in conclusion, that's how we feel about the success of our project, and yeah, thank you.
Yeah, thank you.